Okay, hello. This is the voice of Ms. Fitzmaurice, and today we are going to be talking about momentum and impulse. So I've written the objectives on the screen. I'm going to want to be able to define and calculate momentum and define and solve problems involving impulse. So let's go ahead and start with the definitions so that we know what these two words mean. Okay, let's start with momentum. That's probably a word that you've heard before. So we'll put up the definition and then we'll talk about what it means. So the definition for momentum is very simple. We use the variable p to refer to momentum. And we just say that p equals mv, where m is the mass of the object and v is the velocity. So for base units, we can put m in kilograms and v in meters per second. And so then p, which is the momentum, is in kilograms times meters per second. So when you learned about newtons, you combined a bunch of units to make a new unit, but there's not really anything like this for that. There's not another name for units. We just say kilograms times meters per second to talk about momentum. In common use, you might hear about the momentum, say, of a sports team. You could say that the Giants had a lot of momentum this season. They carried it all the way to win the World Series. So in physics, momentum means more generally just how unstoppable an object is. So just as you can think about the Giants were unstoppable this season, if you think about an object that either has a lot of mass or has a lot of velocity, or both, is going to have a lot of momentum. We're not going to do an example of this because it's just multiplying two numbers, which you already know how to do. So impulse is a little trickier, and we're going to talk about that a little bit more. The definition of impulse, and we use the variable j to refer to impulse. And impulse is all about change in momentum, so delta p. But to explain what we mean by that, we're going to do a little example. So let's say you and your little brother are playing air hockey. So here's the air hockey table, and here's your little brother just chilling out. Okay, and this is a weird version of air hockey, and there's a really giant air hockey puck. And you hit it too hard, and so it's flying at your brother's face. And his shoelace gets stuck to the table, so he's stuck. And so you need to figure out how to stop this air hockey puck. The giant air hockey puck of doom is what I'm supposed to call it. So what can you do to save your brother? What are some things you could do? So I'm going to pause the video, think about what you could do for a minute. What are the different options? Okay, so hopefully you've thought about what your options are. There's sort of two main options that you can do. So one option would just be to, say, get a bunch of your friends and have all your friends apply force to the giant air hockey puck. So they're all pushing on it, and so you apply extra force, and that will cause the puck to stop in time. Okay, if your friends aren't around, then you have to do option 2, where it's just you pushing on the hockey puck, and so you have to push for a longer time in order to slow it down until it stops. So you can either do extra force or extra time in order to slow it down, in order to change its momentum. And so when we talk about the definition of impulse, we're going to talk about it in terms of either extra force or extra time. Okay, so we've said that J is our impulse. That's equal to change in momentum, delta P. Now, previously we defined momentum, P, as mass times velocity. We know that generally mass doesn't change. So we can rewrite delta P as m times delta V. And that's our momentum side. And remember, when we were talking about impulse, we said that in order to get a change in momentum, you can either apply more force or apply it for a longer time. And so we're going to rewrite J as force times time. Now more specifically, we're going to say delta T, change in time, because we want to do final minus initial. And for force, we want the average force over the duration that it's applied. And so if you want, you can say delta T is equal to T minus T naught, and you could say delta V is equal to V minus V naught. And so this is how impulse relates to change in momentum. So we've got this definition. One way to check to make sure that it makes sense is to check the units match on both sides of the equation. So we'll start with the right side since we already talked about that one. Mass is in kilograms, and a velocity, or a change in velocity, is in meters per second. On the left side, this was our definition of impulse, force times time, times force times change in time. And we know that force is in newtons, and time is in seconds. So we should be able to prove to ourselves that those units are the same. And so you should remember that newtons are kilograms times meters per second squared. Because remember, newtons are force, and since force equals mass times acceleration, we know that newtons are kilograms, which is mass, times acceleration, which is meters per second squared. So this is our term for n times seconds. And if you think about it, divided by seconds squared, and then times seconds, well, those are going to cancel out. And so you're left with kilograms times meters per second. And so the units on the left and the right don't match, and so we know that this makes sense as a definition for impulse. The units do match on both sides, so it's good. Okay, so now we're going to do a practice problem to make sure that these concepts are clear. This is on the worksheet that you have that says Impulse Practice Problems at the top, and we're going to look at problem number 4. So problem 4 says a 60-gram egg moving at 4.8 meters per second is going to be caught by a student. And so part A asks, if the time of interaction is 0.25 seconds, what is the average force on the egg? So if we look at this problem, we can see that the egg has some momentum, so it has some motion. It'll take some effort to stop it. And then at the end of the problem, it stops. So we know that there's a change in momentum. So if you think about change in momentum, you should be thinking about impulse. You should be thinking about how to use our impulse equation to answer this question. So our definition of impulse was average force times change in time has to be equal to the mass times the change in velocity. Okay, and so we can actually, if we read the problem closely, we can sort out most of these terms. we know we're looking for the average force, so that's going to be the variable that we're solving for, is the F on the left side. It says the time of interaction is 1/4 of a second, 0.25 seconds, and so that's going to be our delta t. Then on the right side, we know that the mass of the egg is 60 grams, which I'm going to write as 0.06 kilograms, because there are 1,000 grams in a kilogram. Kilo means 1,000. And for delta V, well, let's think about this. We know that delta V is V final minus V initial. The final velocity of the egg, if you think about it, since it's caught by the student, is 0. The initial velocity is 4.8 meters per second. And so now we can pretty much solve this equation. And so on the right-hand side, we'll have negative 4.8 times 0.06, which is going to be negative 0.288, is equal to the average force times 0.25 seconds. So we can divide both sides by 0.25, and we'll find that the average force is going to be negative 1.152, and our units for force are newtons. Note that the answer wound up negative if you did this correctly, which seems sort of weird, but if you think about it, the egg, let's say up in the picture on the top, the egg was moving to the right, and so in order to make it come to a stop, you needed to change its momentum in the opposite direction. You needed to apply a force in the opposite direction. And so it's this average force is negative because it's opposite the original momentum of the egg. Okay, so now part B of problem 4. It says if the maximum force the egg can withstand is 6.50 newtons, what is the minimum time required to keep the egg intact? So this is asking sort of a different question, but it's going to use a lot of the same concepts. I'm going to go ahead and pause the video. I'd like you to try to answer this on your own. I've left the diagram and the equation up to get you started. Okay, so hopefully you paused the video and were able to work out this problem. You may have noticed that since we're trying to find the change in time, this time the right-hand side of the equation, which is the change in momentum, is actually the same from the previous part, since what the egg is doing is still starting at 4.8 meters per second and then coming to a rest. So you could use from the previous part the negative 0.288 kilograms meters per second. And then it's just the left-hand side that is changing. And so you can solve for delta t. You should have gotten that time is 0.043 seconds, which is the time needed to stop the egg with the force required. So now you need to finish the rest of the problems on the impulse sheet, and that you'll probably have some extra time after that, and so you should use that time to work on test corrections. Ms. Fitzmaurice really wants you to use your time wisely, because soon she will be back in school and she will know if you did not.